Hi everyone. For our 450 project, we're doing the single degree of freedom robotic arm. This is controlled with the microcontroller, TIVA microcontroller, and we have an H-bridge driver right here, which is going to control the motor with the H-bridge, and we also have a BJT MOSFET system, which is going to be controlling the electromagnet. So for our 1 degree of freedom robotic arm, we're using the 3.3 voltage output to connect to the 3.3 of the H-bridge driver circuitry. We have ground connected up here from this terminal right here. We're using for HB1, we're connecting PF1 port, which is enabled, which is connected actually from the bottom for the pin. It was easier. We're using PF3 up here for which is connected to the bottom again. For HB2. For the potentiometer, we use port E, PE4, which is connected right here. And yeah, for the MOSFET, we're using PB6 for the control of the electromagnet. So for the hardware setup, we connect the microcontroller to our computer setup over here. And the ports are connected to the H-bridge driver circuitry, which is right over here. Pardon the zoom. So we got ground, we got a potentiometer input, HB1, HB2, the MOSFET, and the 3.3 volt control. On the power side, we have the motor terminals coming in here. We have the electromagnet connected to the input power right here, and we have the potentiometer connections here, and 12 volt input power from here, which is connected to the output socket. The goal of the system is to start from position A, which is right here, move 90 degrees, pick up the magnet, and bring it back as so. So essentially dropping the magnet here. So the logic will be for the electromagnet to move using PID control 90 degrees, turn on the electromagnet, and move back and release the electromagnet. And now we'll have our demo.
Hi, I'm going to be quickly going over the code. So first thing we do is initialize the 2 pins for PWM output. We have 2 pins because one of the pins is responsible for going clockwise and the other one is going counterclockwise. Here we have the code for initializing the clockwise direction. For clockwise we use PWM1, and port F is used for both the clockwise and counterclockwise pins, so we initialize that register. We need to pre-divide the clock because 100 Hertz is actually, it's only a 16-bit timer. So we show the calculations in the report, but the initialization is done here for the divider. And then port PF3 for one of the going clockwise direction is initialized here. We enable, we set up the pins registers so that they have alternate function, in this case PWM, and we first stop the timer to make sure that we don't have shoot through, and initialize the load register for the timer for the value for 100 Hertz. And before we start the timer up down here, we go through and initialize the clockwise PWM signal. So for that we send a clock to PWM5, which is connected to PF1, which we initialize the port here for the alternate function and set it as output. And then we make sure we stop the timer and load the proper register value for 100 Hertz. Finally, once we're back into the PWM motor init after initializing counterclockwise, we set the duty cycle for clockwise and counterclockwise as 0, and start the timers for the clockwise and counterclockwise pins. These functions up here basically so we're not having a normal one where it hits that value and then it toggles the bit. We have it counts up and down. So what we need to do is we need to inverse the value of the duty cycle that is passed into this function. This function takes in a duty cycle in terms of float from 0 to 100, calculates the inverse duty cycle, and then puts that into the compare register for the clockwise pin and the counterclockwise pin respectively. So this is used later on, but we'll discuss that later. Next we go on and initialize the electromagnet PWM signal, which is down here. We first initialize the clock for the PWM and then set up the PB6 to output PWM here, and then we configure the PWM connected to PB6 to output 80 kilohertz PWM and set the counter value at which the PWM triggers. And down here we have another function called setDutyElectro, and setDutyElectro simply takes the duty cycle. This one doesn't count up and down, so for this one we can just divide the duty cycle by 100 and then multiply that by the value we're comparing, the value of the counter when it reaches its 80 kilohertz. So finally, we start the PWM output on PB6. Next, what we're going to do here in main is initialize the ADC. To initialize the ADC, we go all the way down here. We set a clock for port E. We're using PE2 for the ADC, and we activate ADC and configure it for 125K, and then set up the sample sequencer, and enable the sample sequencer here. So after that, we go through our initialization and then we enter into our while loop, which is handled by the state machine function. So in the state machine function, we go through and we move our arm. We use the move arm function, and what it does is it moves it to a target angle, which is defined here, and we define KP, KI, and KD. So if you motors have different characteristics when you're going clockwise and counterclockwise. As such, when we switch from clockwise to counterclockwise, we coded in a custom KP, KI, and KD value in order to make it easier to tune. So yeah, we go through here and then we have a angle to pot scaling, and this determines the value of the pot for each degree. And then we go through and we define the velocity and the error, and while we have not reached our target, which means that our velocity is not sufficiently small and our error is not sufficiently small, we continue going into this loop and recalculating obviously the velocity and the error. So the pot value is gotten in through our ADC, which is using this function right here to read in our ADC. Let me just find it. So this abstraction just makes sure we don't need to rely on our, oh, here it was. This makes sure we don't need to rely on checking the register. So basically what it does is it has a busy wait condition to wait until the conversion from the ADC is done, and then reads in the results, acknowledges the completion, and returns the value. So this function will pause until the ADC has sampled a new value from the potentiometer. And then once it's sampled, it calculates the error, and then it inputs the error into our PID value. So the PID value, PID function, what it does is it takes our KP, KI, and KD values as well as the error, and it uses this function to calculate what the voltage output should, voltage into the PWM signal should be. So it returns a value from -100 to 100. This is to saturate the output voltage of the PID controller. And what it does is it takes the error and it inputs it into this PWM value, and then checks if it's greater than or less than the cap, and then just outputs the value. Also, we're taking a summation of the error for the KI that we for the value that we need to multiply with KI. Both the previous error and the error incremental are set at static so that this function remembers what the previous value was. They are obviously initialized to 0 because in the beginning we have 0 derivative error, and we have, well, for the first sample we have 0 derivative error and 0 integral. And then finally we take the output of the PID function and set the duty cycle based on that. So set duty is basically a function that prevents shoot through. So if you remember the set duty clockwise and set duty counterclockwise functions, this is a wrapper around those functions. And what it does is, if the value of the PWM output changes from positive to negative, it sets both of the values of the pins to 0 until a certain amount of time has passed, and then after that time has passed, it puts in the real values for the PWM pins. So this is all done here. So we always want to have a little wait in the beginning, and then obviously this will obviously take in our PID, and I put in as -400, so we know for sure that is our first call. Previous PID output is initialized to first call, and it's static because we want to remember what the last value of the PID was, to ensure that we're checking if it changes from positive to negative or negative to positive. And if it changes, or it's the first call, we add a little busy wait delay here of 1 second. This ensures that there's no shoot through, and it basically sets both of the pins values to 0 and ensures there's no shoot through to protect our H bridge. And then otherwise, and then afterwards it loads in the proper value. But if there is no change from positive to negative or negative to positive, it basically skips this entire if block and just loads in the proper values for the PWM's pins. So once we have done that, we basically are moving, and then we put in our previous potentiometer value into pot value. This value is used in our velocity calculation, so that's why we need to keep track of it after we have input our PID. So this basically loops until it gets to its target position. So back to our state machine, we move the arm to 194, our target angle, and then we delay for 2 seconds, and then we set the electromagnet's duty cycle to 10%. This basically turns on the electromagnet, and then we delay 2 milliseconds to wait for the electromagnet to capture the magnet, and the magnet, our payload, and we wait for the electromagnet to charge because it is an inductor. And so we wait 2 seconds for that, and then we move the arm back to 104 degrees using these PID values. So this would be our KP, KI, and KD. And then finally we wait 2 seconds and we turn off the electromagnet. So keep in mind that the waiting for the 2 milliseconds, it does it after it's moved to that location. So move arm will only exit when it's moved to the proper position that it got input as the target angle. So yeah, after it moves to the target angle, it will wait 2,000 milliseconds. So yeah, once it goes through that code, it's basically done and it exits main. So thank you for listening, and